over 1,300 times. That's how many times our Earth would theoretically fit into the gigantic Jupiter. But while the colossal gas giant is by far the largest planet in the solar system, it still holds many mysteries for researchers. To finally change this, NASA sent the Juno spacecraft to Jupiter, which has been scrutinizing the planet, the king of our home world, since 2016. In doing so, it has brought to light a series of circumstances that are as astonishing as they are unexpected. A large celestial body, a large mystery. Although we have known about Jupiter since ancient times, and it has been observed by various cultures for thousands of years, many of its secrets have not been solved to this day. What is known, however, is that the planetary giant has an equatorial diameter of a whopping 143,000 kilometers and that it thus reigns supreme in the size chart of our planetary system. In contrast to our significantly smaller earthly home, Jupiter, being a gas giant, has no solid surface. In fact, the structure of its atmosphere was one of the biggest mysteries in modern Jupiter research before the Juno mission. In detail, this, like the polar region and the magnetic field of the gas giant, had only been partially explored to date. And yet, this is just the tip of the mysterious Jupiter iceberg, because when Juno left our blue home planet on August 5, 2011, it had many more exciting mission objectives in its luggage. Incidentally, it's no coincidence that the spacecraft developed by NASA was named Juno. In Roman mythology, Juno was the wife of the supreme god Jupiter, and thus the only goddess who could see through the fog that Jupiter all too gladly used to conceal his affairs and pranks. From a purely astronomical point of view, however, the veil of mist hid no divine alliances but rather, for example, the question of Jupiter's origin, which should be clarified by deciphering the distribution and abundance of water, ammonia, oxygen, and nitrogen in the atmosphere. An apropos atmosphere. Since the gas giant has the densest atmosphere of all the planets in the solar system, Juno should also provide extensive information about the global structure and dynamics of the gas envelope below the cloud cover for the first time. In addition, Jupiter holds a few more mysteries among the colorful, almost parallel cloud bands. To gather new insights into the mass of the core, the convection currents in the interior, and the presence of water in the planet, Juno was tasked with measuring the magnetic and gravitational fields. Our knowledge of the magnetosphere, which, in Jupiter's best manner, is the largest and strongest in the solar system, should also be taken to a whole new level in the course of the mission. So, what has Jupiter discovered in the realm of the gas giant? Jupiter is breathtakingly different. On July 5, 2016, after a journey of almost 5 years, Juno swung into an eccentric polar orbit around Jupiter, and a few weeks later, it performed its first close flyby, passing through the gas giant's cloud tops at a distance of less than 5,000 kilometers. The information and images collected and produced in the process once again left researchers on Earth open-mouthed, because the first Juno data actually did contain some huge surprises. One of them concerned the polar region of Jupiter. The bands of wind that regularly sweep around the planet and give it its characteristic appearance literally vanish into thin air here. Instead, we see huge storm vortices, which can be recognized as colossal spots and splashes. While the storms in the region around Jupiter's North Pole reach diameters of 1,000 kilometers, they can be as much as 1,400 kilometers across at the South Pole. But a glance at the following Juno image shows that these prime val structures are not only scientifically valuable but also have artistic merit. Although the structure initially looks like the work of an abstract painter, it's actually a purely planetary painting. Incidentally, the light blue areas are high storm clouds, which probably consist of ammonia ice and water ice crystals. They tower kilometers above the lower cloud layers, which are colored dark in the photo and even partially cast a shadow. However, the fact that the experts said after their evaluation that Jupiter is breathtakingly different was not only due to such wondrous images but also to the astounding appearance of its polar regions. In contrast to Saturn, there are no pronounced ring currents at the poles here, such as the so-called hexagon. Quite the opposite. Juno could not detect any structure here that would even remotely resemble such a wind pattern. In other words, this means nothing other than that the polar dynamics and atmospheric structure of Saturn and Jupiter must differ significantly. No less astonishing were the discovery of a 7,000 kilometers wide cloud that Juno identified far above the cloud cover of the North Polar region and the thermal measurement data. The latter revealed that the gas flows under the cloud cover are, in fact, distributed quite differently than previously assumed. Instead of a relatively homogeneous ammonia ocean, the gas at the equator forms a giant ammonia column that extends in a ring around the planet. The experts stated that the column-shaped outflow is surprisingly reminiscent of the Earth's Hadley cells, air currents that transport warm, moist air at the equator and allow it to sink again as cold, dry air along the tropics. There was also an unexpected report regarding the magnetic field. The data collected by Juno showed that it's almost twice as strong as previously expected. Furthermore, it also has a clumpy nature. It's more pronounced in some places than in others. To say that the data collected by Juno caused a stir among scientists would, therefore, be an understatement. Just how radically our view of Jupiter has changed becomes clear when we listen to the words of Scott Bolton, the principal investigator of the Juno mission. He said, "The whole thing looks different than anyone would have thought before. I mean, no matter how we looked at it, we were shocked by what we saw. But sometimes, the things you can't see also cause a mixture of amazement and disbelief. Because although the experts had predicted a rocky core the size of Earth for Jupiter, the first Juno measurements simply could not confirm this theory." Scott Bolton was quoted as saying, "We don't see anything that looks like a core. There may be a core of heavy elements, but it may not all be concentrated in the center. Maybe it's much bigger. Maybe it's half the size of Jupiter. But how can that be?" While the Juno mission initially raised more questions than it answered, it was able to shed light on other areas and finally clarify the nature of Jupiter's extraordinary auroras. How Juno solved a decades-old mystery. They are among the most enchanting spectacles that our Earth has to offer, and they are also a permanent feature on Jupiter. And yet, Jupiter's energetic polar lights were overshadowed by huge question marks for decades, mainly because, unlike our auroral ovals between 65 and 80 degrees latitude, they don't reach directly above the poles. But the unusual duration of the light phenomena, lasting several days as seen from Jupiter, also caused headaches for researchers for a long time. A few years ago, Juno, in collaboration with the European XMM Newton X-ray telescope, finally succeeded in uncovering the background to this peculiar phenomenon. After Juno had plunged into Jupiter's magnetic field and XMM Newton had simultaneously analyzed an aurora over Jupiter's north pole, it was clear that the auroras are actually generated far away from the gas giant. More specifically, the oxygen and sulfur ions surf the polar magnetic field lines from one pole to the other, and on this journey, they are accelerated in stages by a special type of electromagnetic wave, which ultimately creates the typical pulsation. The corresponding electromagnetic ion cyclotron waves, in turn, arise in the outer magnetic field region as soon as the solar wind comes into close contact with a magnetic field and compresses it. In the process, energy is released, causing vibrations and catapulting the ions back to Jupiter in spurts. At the end of this process, the incoming particle storm triggers the glow of the auroras. And according to the experts, this fundamental spectacle could also be significant on other planets, such as Saturn, Uranus, and Neptune. The wet gas giant, as briefly mentioned earlier, deciphering Jupiter's origin is also one of the overarching Juno mission objectives. To understand how and from what the gas giant formed, it's, therefore, essential to take a close look at its chemical composition. And that is exactly what Juno did when it studied the cloud cover of the Colossus at close range using its microwave radiometer. In principle, Jupiter's cloud-filled atmosphere does not consist of water vapor or water ice but of frozen ammonia and ammonium hydrogen sulfide. And yet, there are also clouds of water ice here, and more than previously thought. While the measurements of the Galileo mission still indicated that the gas envelope of the planet contains far less water than assumed at the point studied, the observations made by Juno showed that Jupiter's atmosphere, at least at the equator, contains much more water than suggested by the previous data. Since water in the reflected microwave radiation leaves a specific absorption pattern, this also provides insights into the overall water content. And in terms of numbers, this means nothing more than that the water content in the equatorial region of Jupiter is 2,500 parts per million, or, to put it another way, water makes up around 0.25% of all molecules in Jupiter's atmosphere. If the measurements are representative of the entire planet, its atmosphere would contain 3 times more water than exists in the Sun. In view of this surprising finding, Scott Bolton once again expressed his great astonishment. He said, "No sooner did we think we understood Jupiter than it reminded us how much we still have to learn. But what can the values tell us about the formation of Jupiter?" Well, according to the current theory, the gas giant was the first planet to form in the primordial cloud around the young Sun. In the process, it incorporated a large part of the material in the accretion disk. And if Jupiter were to have formed through a partial collapse of the primordial cloud, its elemental distribution should correspond to that of the Sun and the rest of the primordial cloud. However, if the planetary core formed through the gradual accumulation of smaller chunks, these could have carried more ice and thus water. Some formation models can already be discarded based on the new Juno data. But before we can draw a comprehensive picture of Jupiter's birth, a little more patience is required. As already mentioned, we still don't know whether the water content of the equatorial region is also representative for the other areas of the planet. And to clarify this, further on-site measurements are essential. The good news, however, is that Jupiter's successor is already on its way. And if all goes according to plan, the ESA probe JUICE will reach Jupiter in July 2031. Once there, however, the aim is not only to further decode the gas giant but also to clarify whether the Galilean moons Europa, Ganymede, and Callisto are habitable. And our probe has found out that the subscribe button is definitely clickable. Click now on the thumbs up and subscribe to never miss a new video from us again. We'll see you soon.